All right, students, let's dive into Chapter 18, Ray Optics. Now, we've already talked about the different models of light. We said there was the wave, the ray, and the photon model. Of course, this chapter will be looking at the ray model. Now, typically, light rays, based on the source and the shape of the source, but typically light rays, for example, from a laser beam, will follow each other parallel, and they can travel in straight, and they can also cross each other. And of course, when we look at reflection and refraction, of course, we see that light rays will reflect, refract, and scatter, and can be absorbed. And of course, it all depends on the type of interface you have, the angle of incidence, and of course the index of refraction has a lot to do with what will happen to the light ray once it strikes the object. Now, we can treat objects as a source of light because all objects reflect light, okay? And so when or some absorb light, and they of course appear black, but objects give off light. Now, we can treat each point on this Christmas tree as a point source of light, but understand this, and I think I said this in Chapter 17 lecture, that when light travels from an object, it travels in all directions with an infinite number of light rays, okay? So how do we then see objects? Well, of course, the light rays travel from the object and pass through the lens of our eye and focus in the back of the eye. Now, we have, of course, self-luminous objects, which create light, reflective objects. I think that's self-explanatory. Self-luminous, like a star. Those are self-luminous. Light bulbs are self-luminous. And then, of course, objects that reflect, such as mirrors and various reflective films, okay? All right, so we have two kinds of scattering. By the way, and how do we describe light when it's traveling from an object, from the source? We use what is called ray diagrams. We'll get into that in a little bit. We have what is called diffuse reflection and scattering. Now, there's actually two kinds of scattering, Rayleigh scattering and Mie scattering, or Mie scattering. Rayleigh scattering is what we see when we see the sky. Why is the sky blue? Okay, and Mie scattering appears typically in clouds and pollution and that sort of phenomena. Okay, now, all right. So we have what is called diffuse reflection, and of course we have scattering, and we also have well, I'll save that when we get to it. All right. Okay, so we have specular reflection, okay, and specular reflection is when light bounces off of a very smooth surface, like a mirror or a piece of glass or some other type of reflective film, okay? And this is pretty much always a given when we're looking at specular reflection, which is reflection off of a very smooth surface, highly polished surface. It could be a piece of metal. You know, you can polish aluminum and brass to where it will reflect light, okay, and gold and silver. You can really make it shine, okay? Okay, now it's always understood that the angle of incidence will always equal the angle of reflection, and we always measure these angles when we're doing these problems. We measure them with reference to the normal. Now, that's not to say we can't measure it with reference to the surface. We can, but typically when we always take measurements, we reference it to the normal. Of course, the normal is a line 90 degrees to the surface, okay? Okay, so these two angles equal, and they lead to what is called the law of reflection. So the incident ray and the reflected ray are both in the same plane, which is perpendicular to the surface, and the angle of reflection equals the angle of incidence. So there's, the law you can write down. Theta R is equal to theta I, reflection and incidence, okay? Incidence meaning incoming. Then we have what is called, we have specular reflection, then we have diffuse reflection. Diffuse reflection is when you have the light is scattered in all directions when it strikes the surface. Here you see a picture of the light rays bouncing off each of the surfaces, and notice how the surface is very uneven, so you get all kinds of scattering. You get random directions of light rays, okay? Now, why would this be important? Okay, well, if you've ever read a newspaper, this is a kind of reflection we use when reading a newspaper. They don't want you to, they don't want to have glossy pages, all of them glossy, because it's irritating to read, okay? Pages typically in a textbook are produce diffuse reflection. If you've ever felt the pages in a textbook, you can tell they have a little bit of texture to them, okay? Well, that's the reason, is because they don't want the pages to bother you while you read them, okay? So they take advantage of diffuse reflection, okay? Now, a plane mirror, of course, is one in which we call it, it's just a flat mirror, okay? And when you stand in front of a flat mirror or a plane mirror, the object you see is the same size as the object that's being reflected, okay? So in other words, the object size and the object size and the image size will be the same, okay? They are equal. Now, when we look at plane mirrors, when we look at point P prime, this is what we call a virtual image, okay? And of course, a virtual image is an image that is not real, okay? And you say, well, how do you know that? Well, if it can't be projected onto a screen, then it is not a real image. It is a virtual image, okay? All right, so the image distance on a plane mirror is equal to the object distance, okay? So notice how they're equal, okay? Notice how they're equal, all right? Now, and by the way, the magnification of a plane mirror is always going to be 1, okay? It always has a magnification of 1, all right? Now, so plane mirrors, again, the rays, how does this work? Well, the rays are go towards the mirror and bounce off the mirror at every point. And of course, what happens is they reflect back into our eye, and we see the image as it is. Now, what about refraction? Refraction is a little bit different. Refraction is not reflection. Refraction is the bending of the light, or the alteration of the light ray path as it goes into a material. Now notice the incident ray comes in. Notice what happens. You do get reflection. I'm not saying you don't, but notice the bulk of the ray is refracted. So notice how it bent when it came in right here. It comes in, the incident ray, and it bends. All right. That is the refracted ray in the piece of glass. Now, all right, so of course part of the ray does continue, and of course it re-enters back into air, and notice what it does again. At the interface, it refracts again. And what you should notice here is that this angle, well, actually the normal's here, okay, and the normal is right there, okay. All right, so you always measure with reference to the normal. And let me erase that. Okay, all right. Okay, these angles right here are going to be congruent, okay, because it cannot, when the incident ray coming in, cannot refract any greater or less than when it re-enters air. It has to have the same angles. Now, if you pat another material over here and then it comes into air, well, of course, it's still, when it comes in, it's still going to have the same refracted angle. All right, now, all right, so here we see how refraction works. Of course, this shows us that when the light enters, it refracts, it bends. That's what refract means. Okay, and how do we measure the angle of refraction? Well, again, we always measure everything to the normal. Always measure everything to the normal. So we measure unless the directions tell you otherwise. Okay. So here's our angle of incidence, here's our refracted angle, and how do we find that refracted angle? Well, we use something called, and again that's just the same sign, we use something called Snell's law. Wilbrord Snell proposed this equation, mathematical equation, in order for us to be able to determine what our refracted angle is at the interface, okay? And again, measuring with a normal, and it all depends on the different media in which the light ray is traveling through. The light ray could be traveling from air to water, air to glass, glass to air, water to glass, water to oil, okay? It could go from water to oil to glass to air, okay? So it doesn't, the number of mediums are not important, but Snell's law will apply at each interface, okay? It's a very easy equation to work. Here you see the index refractions. We've already looked at some of these. Notice how these index refractions start getting pretty high, okay? All right, now what about total internal reflection? Total internal reflection occurs when the angle of the light ray is at the okay. Hang on a second, y'all. I've got a situation. Sorry. Okay, sorry about that, y'all. I had a situation that came up. Okay, so when we look at total internal reflection, how do we get material to totally internally reflect? Well, the key is that the index of refraction has to be greater than, of the material has to be greater than the material surrounding it, okay? And so in order for it to internally reflect, that's how it has to work. Now notice, well, you say, well, how do we know what angle the object, or what angle has to be, the object has to be set at to get it to totally internally reflect? Well, that is where Snell's law is adapted into this right here, and we say, okay, well, theta 2 is at 90 degrees. Now you say, where is the 90 degrees? Right there. So once we get it to the point to where the angle will reflect at 90 degrees, then anything greater than that, it will internally reflect, okay? So notice that it says here that there's no critical angle and no total internal reflection if N2 is greater than N1, okay? So what you want is you want to have N2 less than N1, okay? And of course, how does that work? Well, your media has to have a fairly significant difference. I say a fairly significant, it doesn't have to be extremely significant, but let's say if it's going from air into glass, okay? Well, then you know that if the angle, the critical angle is correct, then it will totally internally reflect. Or say plastic, like fiber optic cable. And that's basically the premise in which fiber optic works, okay? So notice if the N2 is greater than N1, then it will not reflect, but if N2 is less than N1, then it will totally internally reflect, okay? Now, where do we take advantage of this? Of course, we see it in binoculars. We see the use of binoculars, but the greatest use is fiber optic cable. And of course, here you see the light source coming in, and it tells us that that when it strikes the inside wall of the fiber at an angle of incidence approaching 90, it's larger. This is larger than the critical angle, so it does undergo total internal reflection. Okay? Okay. All right, so to keep it from, to help it maintain this total internal reflection, they put a glass cladding which surrounds the glass core, and of course this causes it to continue to internally reflect. And I tell you here some examples of how we use this, okay, in surgery. All right. All right, now, what about refraction? Again, if we've talked about image formation by refraction, of course we know that's the bending of the light waves. Like we see the ruler there, and you've probably done it with a pencil or your finger or whatever. All right, so what does this mean? It basically says that the ruler appears to be closer to the person's eye than it actually is, okay? And again, why is this? Because of refraction at the boundary. So what we can do then is that we can find the image, we can find the location of the image by taking the angles, tangent of angle 1 divided by the tangent of angle 2 times the object distance, and we can find then the image distance, okay? Notice it shows you here image, and that's object, okay? S prime is image distance, okay? So that's one way to find it, and of course they show you the relation of Snell's law and how that works. So what does this lead to then? We can take this looking at it through small angle approximations, where sine theta is approximately equal to tangent theta, and so we can find then the image distance if we know then the what? The index of refractions and the object distance. So there's another equation. Now let me say this. Does the image and object have to be in meters? No, it does not. Okay, this is one situation where we do not have to have the object in meters. We can use centimeters, millimeters, whatever, okay? Typically it's measured in centimeters, okay? So we don't have to put it in meters. Another place where it doesn't have to be in meters is when we look at thermal expansion, okay? All right. All right, thin ray lenses. All right. All right, so when we look at lenses, one thing we have to do to understand how images form is what we call ray tracing, and that's just a picture of what the image will look like based on the type of lens that we use, okay? Hang on. Y'all, I'm really sorry. Some family stuff I'm trying to deal with. Oh me. It's rough when your parents get old. But anyway, okay. So thin ray tracing. Here we see the two types of lenses, converging lenses and diverging lenses. Now, how do we know? Well, it's pretty obvious. A converging lens is typically what we call a convex lens. Notice it curves outward, okay? And notice how the rays converge at a particular point. A concave lens looks like you're going into a cave. It's curved inwards. And notice how the light rays diverge when light passes through a concave lens, okay? So that's how we determine whether it's converging or diverging. By looking at the curvature of the lens and what do the rays do? Do they converge or diverge, okay? All right, so with converging lenses, we have what is called a focal point, and of course the focal point is the point at which the light rays will converge. And it all depends on what we call the radius of curvature of the lens as to where the focal point will be, okay? And of course the distance from the lens, okay, and this distance is measured this way. We have a line passing right through the middle of the lens. It is measured from that point to the focal point. That's called the focal length, okay? All right, so, okay, let's go ahead and let's look at diverging lenses. Okay, what about diverging lenses? Okay, well, you have focal points here, but they're called far focal points. And believe it or not, you can have a focal point on both sides of the lens. and here with the concave lens or a diverging lens, we can see that the light rays will reflect back to this near focal point, and they appear then, of course, to diverge from that point, okay? So notice it says the focal length, of course, is the distance from the lens to the point at which rays parallel to the optical axis converge or from which they appear to diverge, okay? So thin lenses then are what? They are lenses whose thickness is 0 and that lies entirely in a plane called the lens plane, okay? And with thin lens approximations, all refraction occurs as the ray crosses the lens plane, okay? And they are measured from that plane, okay? And that's what I was just showing you a minute ago. If you look at converging lens, that's the lens plane. These are really good diagrams, by the way, too. And of course, we see the focal point, the focal length, the near and the far focal points and focal lengths, and there are, they should be the same on both sides, okay? And then, of course, the center of the lens, which is the center of the actual lens plane, all right? Now, what do we mean by a real image? Well, a real image, and we always teach this in physics, that a real image is an image, when they interact with a lens, they converge at the image point, okay? And we call that the real image point of point P. And typically we say this: real images can be on a screen. In other words, you can place real images on a screen. Okay? Place real, I don't know why I put a T there, real images on a screen. Virtual images, however, do not or will not transmit onto a screen, okay? And so virtual images then is a point from which the rays appear to diverge, through which no rays actually pass, okay? So here we see real images. This is a real image. Even though it is inverted, it's still a real image. And so we have our object. We have the near focal point. We have the far focal point. Notice how these are the same. We have the image distance from the lens plane to the actual image, and we have the object distance, S, from the actual object to the lens plane. Now, we call this an inverted image, and by the way, height comes into play, and of course that has to do with what we call magnification, the height of the image, and of course the height, H of the object. So there's H and H prime. Okay, and remember, your primes always deal with your images, okay, not the objects. All right, so how would we describe that? We would say it is a real image, it is inverted, and looks like its magnification is reduced. Okay, it's a reduced magnification, all right? So all points on the object that are in the same plane, the object plane, converge to an image called the image plane, okay? And of course, they're showing where the image plane would be. All right, now, so real images, again, even though they can be inverted, they can still be considered real images, and they will project onto a screen just like what we saw there. All right, now, again, here are some good, and I kept this slide in here because of the directions on tracing, and we'll do a problem or two where we actually draw and trace these so you can see how it actually works. Okay, you basically, when you get done, you'll have a drawing that looks something similar to that, except it won't have this many rays on it, okay? All right, and so these are good rules to go by. Draw the optical axis, use graph paper or a ruler. You need to always establish an appropriate scale. What do you mean? Like, if the problem says that an object is 6 centimeters from the center of the lens, and the radius of curve, or let's say 12 centimeters, and the radius of curvature is 4 centimeters, and then you got to find the focal length, and then you have to find the image height, and it tells you that the object height is, say, I don't know, 2 centimeters. Well, regardless of what the dimensions are, you've got to set a scale. You can say, okay, and typically I like to do it a 1-to-1 ratio if possible, but it don't always work that way, because a piece of paper is only so large. And so if you've got images that are way out there like 25 centimeters and you've got to say, okay, or 24 centimeters, you got to say 1 centimeter on my ruler is equal to 4 centimeters in actual length of the problem, okay? So 1 is equal to 4, whatever, all right? So you do have to set a scale. Then, of course, you want to center it on the lens axis. You want the represent the object with an upright arrow at an image distance, okay? Like here you're drawing it, and here's your lens. Well, I drew the wrong kind of lens. So here's your plane. Here's your central axis, and here's your lens, and then here's your object. Well, you want to do this. Well, you want to draw it straight though. Okay, and we're here, and you want to draw it up straight like that right there. Okay, to start with. That's what they mean by that. Okay, and then of course draw your 3 rays. And that's typically, I always draw them with 3. Notice it tells you a ray initially parallel to the axis reflects through the far focal point, and then a ray enters the lens along a line through the near focal point and emerges parallel to the axis, and then a ray through the center of the lens that does not bend. Okay, all right. So typically you draw at least 3, but you can actually draw 4, but I always like to draw 3. All right, so how do we find magnification? Well, here we see that if we take the image height and divide it by the object height times -1, don't forget the negative right there, then we can find the magnification of the image, okay? A magnification, excuse me, of the lens or mirror. Note it'll work for both. Same thing here, we can find the height. Notice that the height or the magnification is equal to the height prime divided by the height. And notice it is the absolute value, okay, the absolute value. All right, now if, notice this right here, you need to write this down. If we get a positive value, it means it's upright. If you get a negative value, then the image is inverted. It's very, 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 very important that you write that down and you remember that, okay? Okay, all right, let's move on. Virtual images, again, are those that will not transmit onto a screen, or a screen could be anything. It could be a sheet of paper, it could be a sheet, it could be a wall, it could be a projector screen. A screen's a screen, okay? So if the image will not project onto a screen, then it is considered to be a virtual image. And notice how the image is behind the object here on this particular situation. And again, notice you see the rays here drawn when we're doing these. Notice the 3 rays. Notice there's 1, 2, 3. Notice it will show us where our actual image should be, okay? And again, we'll do some of these when we work on the problems, at least 1, maybe 2, okay? All right, again, the 3 refracted rays do not converge, therefore they diverge, and this tells us it's a virtual image, but the image is upright, so the magnification should be positive when you do the calculations, okay? All right, let's move on. Enough about the virtual images we've already talked about. Well, what did that say? It says we define the image distance to be negative for a virtual image, okay? All right, notice that, okay? It's negative, okay? All right, so it's important that you understand that. All right, so a diverging lens is one that is thinner at its center than at its edge, okay? And a diverging lens always makes virtual images, okay? All right, okay? Diverging lenses. Okay, so here are diverging lenses. Notice how it is thinner at the center than it is at the edges. Notice it's thin here, thick at the edges, okay? Notice how you get divergent rays, and you always get virtual images. Now, again, follow the same steps. You do trace them a little different for a diverging lens, but it's basically the same principle, okay? And I'm not going to read to you. You can read that. All right, what about image formation for mirrors? We see spherical mirrors. And listen, the rules are pretty much the same. I mean, as far as the sign convention and everything. Notice that you draw the rays the same way. This, again, is a concave mirror. Okay, concave. That's convex mirror. And by the way, you would label lenses that are shaped that way the same thing. You just say convex lens or a diverging lens, and a excuse me. A convex lens is a is a converging lens, and a concave lens is a diverging lens, okay? All right, so notice here how the rays reflect out away, that would produce a virtual image, okay? And we, again, notice how we draw our rays and when we're drawing these, and again, I'll show you when we do this, okay? Notice how we go from the, they'll reflect off a concave mirror through the focal point, very important to remember, okay? And that's what it's just talking about. They'll notice that these angles here should be congruent, the incident should be congruent to the reflective. And so when an object's distance S from the mirror is greater than the focal length, there's 3 special rays are enough to locate its position, and there you go. Okay, well, they actually drew more than 3. All right, so let's look at these drawings and let's see. Okay, again, here's how we draw the rules for drawing. Now, let me say this. I don't know how I want to do this for the final exam. If I want to let y'all write these rules down on your note card, or if I'm just going to give them to you. I'll probably just let you write them down on your note card and just be brief and short when you're drawing them, okay, onto your note card, on your formula card, okay. All right, again, here we see convex mirrors and how the light will behave with a convex mirror, okay. Again, we produce and notice that it is behind the mirror, okay. Well, what kind of image will that be? Well, it has to be a virtual image, okay. Only way it can be, all right. And again, these are the ray tracing for a convex mirror. Again, it's a little bit different because when you draw the rays, notice how they you follow the same principles, but notice how you draw the dotted lines to the image and then you continue the ray on up this way, because that's the way it's actually going, okay? So that's the only difference. There's the rules, and you can write those down, y'all. I'm not going to read to you. You are big boys and girls, and you can read. All right, so the thin lens equation. Here again we see we take what is this, a convex lens or a converging lens, and we want to draw our rays, okay? And typically, as we said, we always take the first ray, bounces off and goes through the focal point. The next ray goes to the center of the lens, and then the next ray bounces back through the radius of curvature, or should, okay? So now, so how can we find then the focal point, or how can we find the height? All right, notice we take our equations, we start doing a horrific amount of substitution, and the equation we finally wind up with is this one right here, okay? Our thin lens equation, okay? So we can take these equations, notice they combine the height and they combine the image distance, object distance, and we come up with this equation. So if we know the image and the object, we can find the focal length. If we know the focal length and the object, we can find the image, and so forth, okay? Very easy to use, all right? And here are your sign conventions, very important to remember. If the focal object is outside, notice that it tells us what? It tells you, like here, the magnification would be negative, it's real, and it's inverted. And so the image distance is positive. Why is it positive? Because it is in front of the mirror, okay? Magnification, however, would be negative because it is inverted, okay? All right? And so that's telling you, all right? Notice here, the image is real, okay? It is behind the lens, all right? It's still negative, okay? It's negative, all right? All right. Okay, and so you can follow these rules for sign conventions and help to understand whether I assign it a positive or negative. Notice these 4 cases give virtual image. They're upright, magnification is positives, and the image distance S is negative, okay? Okay, so you can look at all of those and figure that out. 1, 2, 3, 4, all right? Okay, I hope this helps.